Hi, this is Naman, register number 24BCE5047, and this is my DA3 for Computer Networks course under Dr. SubbuLakshmi ma'am at VIT Chennai. The network parameter I have analyzed is round trip time across low, medium, and high traffic conditions using iperf3, Wireshark, and a Python script I wrote to process the PCAP files. Let me walk you through it. So here is the PCAP analyzer code which uses Scapy to take the inputs from PCAP files and generate graphs upon it. So we can see the extract data RTT samples function. This is the main function. For every outgoing TCP data segment, I record the sequence end and the timestamp. When the acknowledgement comes back from the server acknowledging that sequence, I subtract the two timestamps. That difference is one RTT sample. Then we have extract handshake RTT sample function. If the capture is very little data traffic, the script falls back using the SYN to SYN ACK timing from the TCP handshake instead. Then we have the main function where all the PCAP file is inputted into the code, which infer traffic classes from file name prefix L, M, and H. L meaning low, M meaning medium, and H meaning high. Generates per file RTT trend graph for each and then produces two summary charts plus a CSV file at the end. And here is the vlog. While we see the vlog, we can run the code which will generate all the graphs. It takes a minute or two to generate all the 30 graphs. So we can look at the vlog here. The vlog opens the core argument. The most people treat ping RTT as a fixed property of a link. This DA shows that's wrong. RTT is produced dynamically and it depends heavily on how loaded the network is. All 30 tests were run against iperf.he.net, Hurricane Electric's public iperf3 server, from the same machine on the same link back to back. Split into three classes: low with one stream, medium with 2 or 3 streams with caps, and high with up to 10 streams or UDP floods at 200 Mbps. The baseline. The physical floor of this link is around 250 to 260 milliseconds. That's India to Hurricane Electric server. No optimization can make it lower, but as you will see in this TA, loads can make it vastly higher. So this graph here shows the big picture of the whole DA. It's like a 10-second version of the whole DA. The low traffic bar L1 to L10 hovers near 250 to 400 millisecond baseline, barely visible. Medium splits into two groups. M1 to M4 looks like low traffic, but M5 to M10 jumps multi-second averages. High traffic is uniformly large. The striking observation M9, a medium test that averages 6,886 milliseconds, worse than every high traffic captured. The box plot also confirms it as a tight flat box represents low traffic. Medium is slightly wider, high is completely different thing. The box alone spans 1500 to 5200 milliseconds network load. Doesn't shift RTT by a constant. It stretches the distribution exponentially. Then we can look at some graphs which are generated and interesting. The graph 6 generated by using iperf.he.net at using 10 seconds and 5 Mbps caps. Single stream. The sawtooth between 260 and 340 millisecond is TCP spacing, loop made visible, queue fills, RTT rises, sender backs off, queue drains. Then this whole process is repeated and the jagged tooths are formed. The congestion control breathing. Then we have L9, small buffers. Single stream but 256 byte buffers. RTT climbs past 1100 milliseconds, same amount of data but 10 times more packets. Small buffer punishes the network even under tight load. M5 RTT trend of medium traffic. Bufferbloat ramp. 2 stream 10 Mbps cap. This is the Bufferbloat signature. RTT doesn't spike. It ramps slowly from 300 milliseconds to over 5000 milliseconds across 30 seconds. The queue fills and never drains. M9, which is the worst case here in the whole dataset. Only 2 streams but with a 15 Mbps cap and a 45 milliseconds. Average RTT hits 6808 milliseconds. The lesson here is the right bad parameter at the right magnitude beats the sheer amount every time. Then we can move on to high traffic conditions. H4, the counterintuitive. 10 parallel streams and yet the best traffic result at 1143 milliseconds. Why? More flow means TCP's congestion control fires more often, keeping queues in check. More streams can actually produce lower RTT than fewer. Then H6, the UDP triangle. UDP at 100 Mbps, perfect triangle. UDP has no congestion control. It is pure fill overflow reset cycle. The curve shape is protocol fingerprint. Coming back to the coding part, as we can see, the code has been compiled and all the graphs has been plotted in PNG format, including the summary graph and the box plot. So the main conclusion here is the RTT is dynamic, not static. The ping on the floor is not necessary that it will be available everywhere. It can grow 10 times or even 100 times. Bufferbloat is real and visible. Once you have seen it, you will spot it everywhere. Third, the throughput and latency are in tension. Push either too hard or the other breaks. All 30 pcap files and Python script, the generated graphs and the blog link are in my GitHub profile in the description. Thank you to SubbuLakshmi ma'am, VIT Chennai and Scope for providing me this opportunity.